Hello everyone, the problems that we're looking at today is the USACO 2019 February contest gold and silver of painting the barn. And this is the first time that I'm going to try making a video over two separate problems, but this is because those two problems are actually very closely related. Not only is the title the exact same, but also the technique used in this problem, the silver version, which is 2D prefix sum, is going to be also used in the gold version. So the silver is basically the first step of solving the gold. That's why I'm going to be doing a review on both of these problems today. So first of all, let's take a look at the silver. And after we solve the silver, let's get back to the gold. So first of all, you can take a minute and read through the problem yourself. All right, I assume you read the problem. So basically, you're given a barn that Farmer John is painting, and he's painting the barn so that he's painting them as in like rectangles. So I'm gonna pull up a drawing board here. Basically, you have a barn like that, and you're being told the rectangles that he painted. For example, he painted once in this rectangular area, then you paint another time in this rectangular area, and maybe another time in this one. And now you're trying to determine for how many of the cells in this big barn is there exactly K layers of paint. So say K is 2 right now. Well, then it's only going to be this area with K coats because we have one coat from this rectangle and one coat from this rectangle. However, we can't just solve this problem using brute force. I mean, you can think about it first, but I'm just going to go ahead and say you can't solve this using brute force, and instead you have to use a technique called the 2D prefix sum. As we all know, 1D prefix sum and difference is basically a one-dimensional array, and then you have an array meaning the prefix sum of all these elements, right? And the difference array is just the difference between every two prefix sums, and using that we can find a lot of stuff. So I assume you already know the one-dimensional prefix sum, so I'm not going to explain it here. But the two-dimensional version is basically saying we do basically the same thing except on this 2D grid, and for each cell, for each of the rectangle, instead of actually going through everything in the rectangle and then marking them as painted, we just change the value at right here, and right here. After you change the value at those 4 points, in the end we just take a prefix sum, and then we get to find the number of coats on each cell. And this is going to take us n squared complexity, with n squared being, I'm pretty sure, 1,000 in this problem. Wait, no, not n squared. The range squared. Range is 1,000, so that should be fine. So I'm gonna go ahead and explain my solution here. First of all, yeah, this problem I've done a lot of times, not 2 million, but a lot, because it's pretty basic. It's just the template for 2D prefix sum. So I did it a lot of times, and this is probably gonna be like the 5th, 6th time I did it. Anyways, we input, and then I did x plus plus and y plus plus so that we don't have negative array subscript. Because think about it, when we do prefix sum, we'll do I minus 1 and j minus 1. And if we have, since x and y and x2 and y2 can all be 0, if we have 0, then we have to check whether I is 0, and we can't do minus 1 if it is, because then we'll have negative array subscript. So that's why I did x plus and y plus. And now, the reason I don't do x2 and y2 is because there's actually a trap in this problem, because you might notice that you might think, let me pull back my drawing. You might think that, say, this is x2 and this is x, and this is y, and this is y2, right? You might think that this point or this entire row, this entire column at x2 and y2 is painted, but that's actually not the case, because x2 is not actually painted. It's actually go from x to x2 minus 1. That's the x coordinates painted. And the same with y. It actually goes from y to y2 minus 1. So that's why I didn't do y2 plus plus or x2 plus plus. So when we do the prefix sum difference, we wouldn't have any mistakes. And then it's 1,001 because we did x plus and y plus. And for the 2D prefix sum, we just find, okay, I should actually explain this. So basically, let me just have one rectangle, this one, right? And we know that when we take 2D prefix sum, we want to change the values at these 4 points, but by how much? And after changing the value, how do we know how to find the prefix sum? So first of all, on a difference array, the way we should modify it is at this value, we mark code number plus 1. And at this value, and at this point, the point right outside of the grid, the point that's not painted, we mark minus 1. This, we also minus 1. And right here, which is also outside of the grid, not painted, we also plus 1. And I'm going to explain why. So first of all, you have to understand that when we find a difference array, what do we do? basically, say we want to find how many codes are right here. We do the difference array of I minus 1j and the difference array of ij minus 1. However, when we add those up, we notice that there's a duplicate area. This area is counted twice, so we have to once again subtract I minus 1, j minus 1. And that gives us the value on all those points, and then we add the value, the difference array value on this exact point ij. So from that, we can find the prefix sum at every point. And we notice that once we get outside of the grid, it's not painted. So we have to use some method to make sure that this plus 1 is eliminated. So what we do is we add a minus 1. So that when we reach this point, we have a plus 1 and a minus 1. And when we add them together, we have 0. And that's what we want. Same with over here, right? Plus 1 minus 1, we have 0. However, when we get to here, we notice that we have 2 minus 1 and only 1 plus 1. So in this case, this point will be thought of as negative 1, but it's actually not true. That's why we add a 1 here, because starting this point, every point beyond it will be added by both this negative 1 and this negative 1. So in order to eliminate them and not have a negative number, we do a plus 1 right here. So that's basically the main idea of 2D prefix sum. And the implementation is once again right here. So now you can understand why we did xy plus plus and x2 plus 1 y and y2 plus 1 x is minus, and then why this one is plus. And that's the same idea. When we find the prefix sum array, it's just I minus 1j, ij minus 1, and then we subtract by the duplicated area. And the answer is added if this point is exactly painted k times. And now we output the answer. Alright, that was it for the silver version, and now to the gold version. And the gold version of this problem is actually very, very difficult, a lot more difficult than the silver one, as the 2D prefix sum, which is all the silver one is about, is just going to be a tiny, tiny pre-processing in the gold one. So let's take a look. You can pause the video once again and look at this gold problem statement again. And this time, instead of just finding how many areas are covered by k coats of paint, you're trying to paint 2 extra rectangles so that the maximum number of grids are covered by k coats of paint. And everything else is basically the same as the silver version. So you can pause the video again and maybe give this problem a try. Okay, so it's alright if you didn't know how to do it, because this one is actually really, really difficult, and I'm just going to explain how I did it here. So first of all, we notice that there's only 2 rectangles that we can paint. So I'm going to once again draw something. Alright, there's only 2 rectangles that we can paint. So say this is a big barn grid, and we already have several rectangles in there. I'm just not going to draw. Since there's only 2, and a very, very important condition in this problem is that the 2 rectangles cannot cover each other. Okay. Are disjoint. See, not sharing any positive amount of area in common. That's actually very important, because now we know the 2 rectangles must be something like that. Like if this is the bottom right corner of the first one, and this is the top left corner of the second one, they must either be like that or like that maybe. But anyways, we know that the top left and bottom right corner have to have a relative position like that. Like that is not legal, right? So if we already know the top left corner, all we have to do actually is to find the optimal bottom. If we know the bottom right corner, of the first rectangle, we know that actually all we can do is to find the optimal top left corner of the second rectangle using a prefix max on this area and a prefix max on this area, right? Because we know that any point in those 2 areas can serve as the top left corner, while this point is the bottom right of the first one. So now the problem is, how do we find, first of all, the optimal rectangle when we paint any point as the bottom right corner, right? Because we need to know the optimal when we use this as the bottom right. And also, how do we find the prefix max, or 2D prefix max of a given top left region, of a region with a given top left corner, So that's basically the main problem. And the hardest part actually is just going to be, for any top left or bottom right corner, find the optimal sub-rectangle with this top left or bottom right at that exact point. And basically, how we're going to solve it today is using a technique called the maximum submatrix. Alright, so the maximum submatrix is kind of like a DP. So I'm going to explain it here. First of all, let's think about what's the naive way of finding. Let's just use bottom right as the example, because top left will be really similar. So let's think of a naive way to find the maximum rectangle stationed with its bottom right at the point ij, right? And we notice that the naive way have an n to the fourth complexity as we just iterate through basically any the x coordinate of the top left corner of this rectangle and the y coordinate of the top left corner of this rectangle. And for each of these possible coordinates, say we use this one as the top left, we find how many k are over here. This one as the top left, how many are over here. This one, you get the idea, right? And we can use a prefix sum array to find that. So this is going to be n to the fourth complexity. However, n to the fourth is not acceptable for this problem as we have the coordinate in the range of 200. So we need to use a better way. And the way for this problem actually is going to be kind of like a DP. If you know how to find the maximum subarray, no, actually maximum substring, you actually know how to find the maximum submatrix because it's really similar. And this time, instead of having I and j, we're gonna have I and k as the x and y coordinate of the bottom right corner. And we're gonna also iterate through the x coordinate of this optimal one, the x coordinate of the top left of the optimal matrix. And this already gives us an n squared and n cubed complexity. And to not have it n fourth, which is not acceptable for this problem, we need to use a method that can help us determine the optimal y coordinate for this given x coordinate in O1 or log complexity. And the DP way is actually just doing, since we have this is k, right? Obviously, this is I, this is j. We first finding the answer for k minus 1. Let's call it BR, right? BR is the optimal station at this point, BRIK. We first find BRIK minus 1. And now we realize that this is actually a lot like the maximum substring one. Because now we have two options. We can either start a new subrectangle with just a width of 1 and a length of I to j, or we can connect this last column to the previous k minus 1 columns, right? Even though it might not necessarily be k minus 1 columns, it could just be one column because that could be optimal for k minus 1 or it could be 2, but it doesn't matter. So basically we use the optimal answer for I k minus 1 and decide whether we add this column to k minus 1 or not. And we can find the number of extra k's that we will have by painting this column easily by just using a prefix sum. And it's not even 2D, it's just 1D prefix sum. All right, so knowing this actually allows us to find in n cubed complexity, when any point is the bottom right, what is the maximum number of k layer painted cells we can have for any rectangle. So knowing this, we can also just use the exact same technique to find that for top left. And finally, we just use kind of like a 2D prefix max array. And for each top left that we iterate, find a prefix max of all the bottom rights that are possible for this top left. So here is my implementation. All right. First of all, this OP is like the 1D prefix sum, even though it looks like it's 2D because it's two-dimensional. It's actually just one dimension because, as you can notice, it's just I that's being subtracted. The J doesn't actually change because we're just finding the prefix sum for any given column, every row, the prefix sum on every row. And basically what this does is if this is equal to k minus 1, we know if we paint this one, we'll get an extra k. And if this is painted k codes already, then if we paint this one, we're going to get k plus 1. And that decreased our answer by 1. So after knowing that, LYC, this is like the decision-making process of DP, because obviously if it's less than 0, we don't want to connect to it. Otherwise, we want to connect to it. And LYC plus, this is the value of the last column, and we take the max of this or with the other j, because right now we're iterating through every single j, so we had to take the max for every single j. After finding BR, TL is also very similar, except this time the OP is bottom to top instead of top to bottom like last time. And the TL is found using a similar process, except this time it's k plus 1 or k minus 1. And finally, BRM is just a prefix maximum. 2D prefix maximum, we just find the maximum value. And finally, notice that we actually have to find the answer for just painting one rectangle, because sometimes painting two is not optimal. So we iterate through every rectangle with top left at ij and bottom right at ij, and original is just without painting any, how many are there? And max BR is, as we already said, taking the prefix max of, say we have the top left at this point, taking the prefix max top left of this region and this region for all the BRs. And finally, we output the optimal answer. However, there's one bug that I made that cost me like 50 some minutes. Is that since now to avoid negative array subscript, we did x plus plus and y plus plus, we actually have a problem because, as we have discussed in the last silver problem, when we paint a rectangle like this, the last row x plus 2 and the last column y plus 2 are actually not painted. They only goes to x plus 2 minus 1 and y plus 2 and y2 minus 1. So we have to take mx is max x and y is max y. We have to take the min of that with 200. Okay, this problem is really, really complicated, and if you didn't understand it, I strongly suggest looking at the code that will be posted in the comments below. I have a lot of explanation in the code, and I hope this problem helped. Thank you so much for watching. Bye. Alright, that was the problem review of today, and here comes grind report. And actually, it's going to be grind report of yesterday, because as many of you might have already noticed, I didn't actually post the video yesterday, and that's because my mom shut off internet too early, and I didn't have time. But anyways, this is going to be the grind report for yesterday. And yesterday, basically what I did was I mocked a contest. I think it's the 2022 December. So it's going to be this contest. And I mocked the silver, actually, of this, because, the new gold ones are way too hard. But the silver, all through the problems, I'm pretty sure back in 2023, I actually looked at them. Like, I thought of, like, I gave them a try, but I never actually wrote out the full code. Like, I looked at the solutions and just, like, understood them. So I still remember some things from them, but the barn tree was able to be solved pretty quickly because it's pretty easy. So it's 30 minutes, pretty good. It's just a simple DP on tree, right? But I don't think USACO will ever give us problems of that difficulty in silver ever again. This is way too easy now. There's no thinking at all. And the circular barn is a lot better. An hour and 24 minutes, and I think it's actually difficulty is actually right. So it could appear in these contests like the difficulty, but so basically is a game theory, and the game theory of this problem, I already solved it, but I haven't logged in. Anyways, for this one, you just have to notice that a few positions is the second hand always win, and a few positions the first always win, and then we find that each farmer wants to stall time as long as they can for a room that they never win, and want to win as fast as they can in the room that they always win, that they're guaranteed to win. And we just find that whichever farmer wins first, right? And it's a lot more difficult, but I was still able to solve it in contest. And the last one actually is, I don't think it's harder than the second one, but I somehow wasn't able to solve it. I made basically all the observations needed and just couldn't solve it. I don't know why. And I also did the log loop P1250, which is basically the exact same as USACO 124 deforestation. And I realized I actually did this problem before the December contest. It was probably back in 2023 or something. That's why I was able to come up with the first observation in contest so quickly. The observation of sorting by right coordinate, the sorting by right region, and growing trees towards the right side. That was probably the reason, even though I didn't realize it in the contest at the time. And this code, I just basically copied it from the 2024 December, except it still took me an hour to debug. I don't know why, because I didn't actually copy. I was just like trying to remember the code, and I couldn't. So it took me an hour to debug, but it doesn't matter. Yesterday I grinded for about 5 hours. Not at all good enough. Couldn't even solve range reconstruction. Really bad. I'm probably not gonna pass this January, but I don't know. All right. Thank you for watching. Bye.